be like a 1 day thing. The notes might be a little bit long because there's a lot to them, so it might spill a little bit into Monday, but then we're still going to do the review, and I'll give you a take-home quiz on Monday for the second section. All right, so in the first section, we talked just in general about sampling distributions, right? How to make them, what they are, what they tell us. Now, the next two sections, we're going to dive into the two specific kinds that we're going to look at for basically the entirety of second semester. Okay, we're going to talk about proportions in this section, means in the next section. So, we're going to suppose that a large candy machine has 15% orange candies. The following shows two simulations. The right simulates taking samples of 25 from the machine, and the left shows taking samples of 50 from the machine. Okay, so again, not actually sampling distributions, but we're simulating that those sampling distributions. Again, one taking 25 at a time, finding the proportion of candies, and then taking one that has a sample size of 50 and finding the percent of orange candies. So first, let's discuss the shape, center, and spread. Actually, a better word would be compare the shape, center, spread of these. So let's do a comparison, all right? First of all, compare the shapes. What general shape do both of these have? They both look approximately normal, don't they? And again, I do appreciate that you need to say approximately because they're not perfectly normal, are they? You would actually get docked points for that if you said that on the AP exam. This is only approximately normal, not actually normal. What about the centers? Where are the centers of both of these? Yeah, I know it's a little fuzzy. Is it 0.15 that it's supposed to be at? Yeah, and both of them share that center, right? Because both of them are trying to mimic the same population, so it makes sense they should be centered at the same location, right? So both have a center at 0.15. What about the spread? Now, this is a little deceptive because the scales are different along the bottom, but what do you notice about the spread of the smaller sample size versus the bigger sample size? Which one has the smaller spread? Again, it's a little deceptive because of the scaling. Here, I think actually the right one has a smaller spread. Again, look at the scaling along the bottom. Again, I know it's kind of poor to make a comparison when the scales aren't the same, but remember a larger sample size. Oh wait, I'm sorry, left-hand side. Did I phrase it? Oh, I phrased it backwards up here. That's what happened. Yeah, so the one with a sample size of 50, that one is going to have the smaller standard deviation. Remember, the bigger the sample size you take, the less variability in that sampling distribution, the less spread there is. Okay, I'll go get one for you. Now, another skill yesterday, aside from just describing these sampling distributions, remember another skill in the section was determining how rare something is, right? And that's what we actually use these sampling distributions for. We use them so when we take an actual sample, we can examine how rare is that outcome of the sample, so we can assess if we believe the claim that was originally being made. So, for a sample size of 25. Would we be surprised to get 8 orange candies from a sample of 25? Well, isn't this one showing us a sample of 25, right? This left-hand side, again, I noted it wrong up above, and I apologize. Would we be surprised to get one that had 32% orange candy? So 32% would mean that we would be getting an observation up here. Would we find that surprising? Would it be weird in that sample size to get 32% orange candies? Yeah, we would find that really surprising because, again, you're noticing that observation is in the tail of the sampling distribution. Okay, so it would be very surprising. We'd be shocked to get that many orange candies from that sample. Here, give me 1 second so I can shift it up for you. Our next question, part C, which would be more surprising? Getting a sample of 25 that are 32% orange, or a sample of 50 that have 32% orange? So let's compare these graphs. So here, for a sample size of 50, to get a sample of 32% orange, wouldn't that be way over here? Looking at sampling distribution, is that really even possible according to the sampling distribution? Are you ever going to see a sample size with 32%? No, you're not. So having a sample size of 50, it becomes even more unlikely that you're going to get a sample with 32% orange, which if you think about it kind of makes sense, okay? Because didn't we say the larger the sample size, the less variability it is? So as we take bigger and bigger samples, wouldn't you agree most of the distribution is going to be closer to the middle, closer to the center? Where's the center here? 0.15. So as you get a bigger and bigger sample size, wouldn't you agree, wouldn't it be much more unlikely to get extreme observations, such as 32%, when the center is down at 15? So there's one thing that you're going to want to pick up on and note, okay? That the bigger the sample size, obviously you know the less variability there is, but because of that, extreme values become much less likely to happen with larger sample sizes, okay? You're not going to see those extreme values anymore like you do with smaller sample sizes. And here, if you want to write it out how I did, there's the typed up version for C. Now, if you notice, the last section was all pretty conceptual, right? Just trying to understand the ideas behind sampling distributions. Well, now that we're specifying that we're talking about proportions, there actually is some math that we're going to be doing in this section to calculate the features of that sampling distribution. All right? So, both of these were only a simulation, however, right? They're not the real sampling distribution. So to look at the real sampling distribution, that's what we're going to do the rest of the chapter, or the rest of this section, okay, is assuming we actually had the real deal, the entire sampling distribution, we're going to talk about the features that it would have, okay? First off, the center, okay? So the center of the sampling distribution, well, to be unbiased, shouldn't the center of the distribution be wherever the population parameter is? Right? Wouldn't that make sense? That's what we said yesterday and the day before. That is unbiased. So the center of our sampling distribution, which we note as the mean of p hat, the center of all of those sample proportions, should be where the parameter is. Now, in this case, for the samples of 25, what did we say the parameter actually is? How many orange candies are supposed to be in that machine? What percentage? 15%, okay? So the mean of that sampling distribution, if we had every possible sample of size 25 and we made that sampling distribution, the center of that distribution, okay, the mean of all of those p hats, that center should be at exactly 15%, okay? The sampling distribution should mirror whatever the population parameter truly is. Now for spread. Spread is going to be a formula that you need to know, okay? So to calculate the standard deviation, this is the formula to calculate standard deviation. Now, on the bright side, that is actually in that formula packet for you, okay? You don't have to have that memorized. You just have to know when you're supposed to be using it, okay? So if we're looking at a sampling distribution of a proportion, this is how we can calculate that standard deviation. Okay, now there is one condition that goes with that. This formula only works if we meet what's called the independence or the 10% condition. Okay, what that means is our sample should actually be less than 10% of the total population. Because if our sample gets too big, if the sample is too much of the population, now we can't say that the individual members of that population are independent from each other. But if it's under 10%, if we're less than 10% of the population, we're going to say good enough. Okay, they're independent enough that this formula should work. Now, we did say that this was a big candy machine, right? So if we're taking a sample of 25, is it reasonable to believe that 25 candies is less than 10% of a huge candy machine? Is that a reasonable belief to have? Sure. Less than 250 pieces of candy in the whole machine, more than, sorry. I think that's reasonable, okay? That this sample is under 10% of the overall population, or in this case, of all the candies in that machine. So again, you'll hear me call this two different things throughout second semester. You'll hear me reference this as our independent condition, but sometimes as a nickname, I also call it the 10% condition. You'll kind of hear me go back and forth between both of them, but just note they reference the same thing. Okay, so that's a condition that needs to be true in order for this formula to work. Now, as long as it is true, we're free to use that formula. Okay, so the standard deviation of our sampling distribution, therefore, would be the population parameter. Well, in this case, what did we say that is? What's the population parameter? How many actual orange candies are there? Or sorry, what percentage? 15%, okay? So we would take that 15% times its opposite, right? So 85, divided by the sample size, okay? And in this case, which sample size did we say we were specifying right now? Which one are we focusing on? The 25. And if you type that in your calculator, you'll get 0.0714 for your standard deviation. Now, this is another way that it kind of makes sense. In the formula itself, can you see as sample size gets bigger, standard deviation is going to go down? Doesn't the formula show you that itself, just the mechanics of how the formula works? So that's another way to understand what we were seeing yesterday and the day before, that bigger sample sizes lead to less variability, okay? Not really. Sorry. Can I come down during lunch, during fourth hour? Yeah, okay. All right, so we have the center, we have the spread, or in this case, we're always going to be referencing standard deviation. The final piece, when we're trying to describe a distribution, the final piece is the shape. And we've kind of already talked about this. What shape are all of these sampling distributions going to take? Approximately normal, okay? So that's the goal. Literally almost everything but one chapter of second semester, all normal things, okay? Now, just like with standard deviation, we had a condition that we had to check in order to use this. There actually is a condition we have to check for saying something is normal, okay? We need to determine if n times p is at least 10, and if n times 1 minus p is at least 10. Or most of second semester, what you'll hear me say is in the sample, the number of successes in the sample, number of failures from a sample. Again, that'll make more sense as we dive deeper into second semester material. But these are the two things right now we need to check to establish that we can say that this is good enough to be considered approximately normal. So what this means is in a sample of 25, we would say 15% of them should be orange, right? In for this one, we would say 85% should not be normal. Or, sorry, should not be orange. Now, what do you notice? Can we say that the sampling distribution is actually going to be normal or approximately normal? Did it work? No. Here we didn't have enough here. And the n times p, the sample size times the true parameter, that wasn't big enough. So in this one, actually, we wouldn't be able to justify saying it's approximately normal. Okay? We're actually not going to be able to say what it is for sure, but it's not normal enough for us to actually do this. Okay? So, I'm sorry, this actually should have been down here for part F. But for this one, we would not be able to say that it's approximately normal. Well, let's take some time. Let's move on to talk about ones that actually are. Okay, so we can actually continue doing the math, work through everything that we need to. So the next example, let's say about 75% of young adult internet users watch online videos. Suppose that a sample survey contacts 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. Describe the shape, center, and spread of the sampling distribution in p hat. Be sure to check any appropriate conditions. All right, so here are 3 things that we need to say and check anything along the way that would justify what we're saying. Now, first, let's just go in order. It says describe the shape. Well, in here, really only one shape matters. What's the one shape that matters? If it's normal or not, right? That's really the only thing we need to care about. Is it normal, or is it approximately normal? Is it not approximately normal? And those are the calculations that we had just done, right? Wouldn't that be checking the sample size times the actual parameter, and then it's opposite, okay? So if you're checking to see, is this actually going to be approximately normal? These are the 2 things that you have to calculate for me, the 2 things you need to check. So 1,000 times 0.75 gives me 750. 1,000 times 0.25 gives me 250. So did it work this time? Can we say that this is approximately normal? Yes. Why? Because both of these are at least 10, all right? So when you're having this conversation, you do need to actually note that as well. So you can say it is approximately normal. Because these are both at least 10. Okay, you do have to give the reasoning. Just showing these 2 calculations actually doesn't count for them. They want to see that you've also checked, hey, I know they're both at least 10. That's what I was really looking for here. So we did shape center. Well, remember, the center of the sampling distribution should theoretically be wherever the population parameter is. Where's the population parameter? What did they tell us is the true percentage? The 75%, yeah. So if we're looking for the center, the mean of all those p hats, the center of this distribution, should just be at that 0.75. And finally, spread. Well, when they say spread, what do they really mean in this case? What do we know how to calculate? Standard deviation, yeah. So this is asking for standard deviation, which again is just a formula that we can use, right? It said take the parameter value, the opposite of it, and divide by the sample size. Again, you don't have to have this memorized, okay? This is going to be in your formula packet that you get. So you just have to know when to use it. You don't have to have memorized what it actually is. When you do this calculation, 0.75 times 0.25 divided by 1,000 gives me 0.0137. And there actually is a condition tied to that. On the previous page, what did we have to do in order to say that this formula was working accurately? What did we have to assess? The other thing. So that our sample was less than 10% of the general population. So going back and looking at this, is it reasonable to think that a sample of 1,000, is that less than 10% of all young adults that use the internet? Is that a reasonable assumption to make? Yes. Okay. So you also want to note that. It's reasonable to believe our sample is less than 10% of all young adult internet users. Okay, so that's what it would look like to fully answer the question, answering the three pieces and checking those two conditions that go along with it. Yes.
That formula is under a binomial distribution.
So actually, the rest of the semester, or the rest of the year, we actually get to work on this page. So that's where it's really coming from. But great observation, though. Now, let's think about how this formula works, okay? So this was a sample of 1,000, right? And they want to know, well, what if we used 9,000 instead of 1,000? So inherently, don't we recognize that that's going to decrease the variability, right? Like by a lot, okay? Now, look though, the sample size is inside a standard deviation. Or sorry, inside of a square root. So it's not going to actually decrease it not by 9, is it? Because that's inside the square root. If I increase this to be 9 times bigger, because that's in the square root, how many times smaller is my standard deviation? Because that 9 is inside of a square root. 3. Okay, so just something to keep in mind. Is when we're talking about altering standard deviation, okay? Well, actually, I'm sorry, this was altering the whole thing, wasn't it? Is standard deviation, if it's 9 times bigger of a sample, because that's inside of a square root, that's actually just 3 times as small of a standard deviation. Two things that won't change, though, okay? The shape won't change. It'll still be approximately normal. And then we talked about yesterday that increasing sample size doesn't change how biased it may or may not be. So it's not going to change the center of the distribution either. The only thing that changes with sample size is going to be the standard deviation. It'll still be approximately normal. It'll still be centered in the same place. Just the standard deviation will decrease. All right, so now knowing how to describe these distributions, knowing what happens when we change the sample size, the next thing to talk about is we can calculate probabilities, okay? What are the chances of getting a sample larger than something else, smaller than something else? Now, what shape is this distribution? It's approximately normal. Okay, so we're dealing with a distribution that is approximately normal, centered at 15%, and has a standard deviation of 0.0137. So if we're being asked a probability of something that's normal, what do we do? Yeah. Any normal probability calculation. Remember that process? So that process is going to be key throughout this chapter. Whenever we're dealing with normal things, again, we know that this process is what we can follow whenever they ask us a probability question involving these things. Okay, so this is my distribution. I'm interested in, oh, I'm sorry, not points. Isn't this 0.75 this time? I'm sorry. I was still I was thinking of the previous example. Yeah, sorry guys. I'm sorry. Okay, otherwise 77% would be nearly impossible if the actual one is 50. All right. So here, this is the observation we're interested in, right? 77%. We want to know how rare is it to get that kind of sample, okay? Or more than that. So if I'm typing in my z-score, that's my observation. Our true center, the prompt told us, should be at 0.75. Standard deviation, we calculated to be that. And that's going to be 0.77 minus 0.75 divided by that standard deviation. That's going to give me 1.46. And once we have a z-score, where do we put it in the calculator? Normal CDF. And because we're looking for more than, wouldn't we start at that z-score and just work our way upward? That's going to give us 0.0721. So about a 7% chance. Now, something just to give you a heads up, okay? Just a heads up. When they do multiple choice, sometimes they kind of leave it in its giant kind of formula structure. So wouldn't you agree? Again, this does not matter on an FRQ. This is just in preparation for multiple choice. Wouldn't you agree that to make that, wouldn't another way that you may have to write that, isn't this where that came from? So just be aware that you may have to recognize this if they leave it in its giant formula format, because isn't that where this bottom came from? So again, FRQ-wise, doesn't really matter. What we just did is awesome, but the green is just to prepare you in case the multiple choice were to do that to you. Okay, just a heads up for that. All right, the Gallup poll asked a random sample of 1,785 adults whether they attended church or synagogue during the past week. Of the respondents, 44% said they did not attend. Suppose that 40% of the adult population actually went to church or synagogue last week. Let me have me the proportion of people in the sample who attended church or synagogue. Describe the sampling distribution and check any conditions. All right. So, remember, our sampling distribution, this distribution itself, is based on what is considered to be the truth, okay? Which of those values are we told to assume to be the truth? The 40, right? Isn't that what they're telling us is the truth, okay? So when we're doing these calculations, isn't that actually what we're going to be using? We're using what the population parameter should be at, not what our sample is telling us, okay? So make that is a very clear distinction you need to make. This is all based on what they're telling us is true right now, not what our sample gave us. Our sample comes in later, okay? So to assess if this is normal, isn't that where we have to check this? If the sample size times that proportion, and the sample size times the opposite of our proportion, if those are both big enough. And in this case, they really should be, but we still need to show the numbers. 714 and 1071. So can we say that this sampling distribution is approximately normal? Yes. Why? Because they're both at least 10. All right, where should the center of my sampling distribution be? Point 4, the center of my distribution should be exactly where the population parameter is. If my sampling distribution is doing its job, if it's unbiased, it's going to be sitting right there where it should be, right? And then finally, standard deviation, that formula says take that proportion, the opposite of that proportion, and divide it by the sample size. 0.0116. And what needs to be true for that to be accurate? What are we technically checking along the way? What? Less than 10%. So let's take a look. We need to actually explain that in context. You cannot just say less than 10%. That doesn't cut it. We have to actually talk about the context of this. So, they sampled just adults, right? They had a random sample of adults. Is it reasonable to think our sample is less than 10% of all adults out there? Is that a reasonable assumption? In fact, isn't that basically a fact? Yeah. Our sample is less than 10% of all adults. Okay, you do need to kind of reference it in context what your sample was. And here our sample was honestly just adults. Okay. So, find the probability of obtaining a sample of those adults in which 44% or more say that they attend church or synagogue last week. Do you have any doubts about the results of this poll? All right, so now we did a sample, okay, and now basically isn't B asking us how rare is a sample, right? If it truly is at 40% of people go to church or synagogue each week, how rare is our sample of getting 44%? So we know our distribution is normal, centered at 40, standard deviation of this. Now, because we're doing a normal probability, what process do we follow? Yeah, we follow this process. Okay, so step 1, let's find the z-score. So the observation is going to be 44% minus the actual mean divided by that standard deviation, and that's going to give us 3.45. Now that I have a z-score, where can that go in the calculator? Normal CDF. And it's that or more, so wouldn't we start at that value and just head upwards, right? It is going to be a very small, yes. Oh, it's even one of the weird scientific notation numbers. 0.00028. So really, 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 really rare. Would we doubt the outcome of this poll then? If we know for a fact that it is supposed to be 40%, yeah, this would be a very, very strange poll, right? We would be very surprised. We would doubt the outcome of this poll, okay? Again, because it is so utterly rare that this would have happened. Apparently. All right. Let's look at our next piece. So what sample size would be needed to reduce the standard deviation of the sampling distribution to 1/2 of the value we found while calculating it in Part A? Okay, so first, just to make sure the number we're going to produce makes sense, if we're trying to decrease standard deviation, what's going to happen to sample size? It increases. All right. Now, we can actually find the very specific amount here. So we're trying to reduce it by 1/2, okay? But remember, because of that standard deviation, doubling sample size doesn't reduce standard deviation by 2, right? Remember, increasing it by 9-fold only divided standard deviation by 3, right? So if we want to cut it down by half, how much bigger of a sample size do we need to make that happen? 4 times as big, okay? Because that 4 going into the standard deviation formula, going into the square root, would reduce it by half. So here, the sample size we need would have to be 4 times bigger in order to cut the standard deviation down by half. So 7,140. All right. So, a little multiple choice practice. Suppose we select a simple random sample of size 100 from a large population having proportion p successes. Let p hat be the proportion of successes in the sample. For which value of p would it be safe to use a normal approximation of the sampling distribution of p hat? All right, so remember, to assess if it's going to be approximately normal, if it's good enough to be approximately normal, aren't these the 2 things that always have to be true? Aren't those the 2 things that have to be true in order to consider it as approximately normal? So we know our sample size, right? We know our sample size is 100, okay? So if the proportion, if p were 0.01, 100 times 0.01 gives me 1. Is that big enough? Is A going to work? No, it's not. So if this were the actual proportion, that wouldn't work, okay? Our condition wouldn't be met. 1/11th. All right, well, sample size of 100. Let's check 1/11th. So 100 times 1/11th gives me 9.09. Is that big enough yet? No, it's not. 0.85. All right, 100 times 0.85 gives me 85. Well, that's awesome. But if it works here, doesn't it also have to work here? Shouldn't we check both of them, right? So 100 times 0.15, hey, that still gives me 15. Did letter C meet both of my criteria? Yes. So is C the answer? Yes. Now, best practice, what should you still do? Check the other 2. I'm not going to waste your time doing that with you right now. But theoretically on exam day, you would want to check every single answer to convince yourself you have the one and only answer, right? D and E would not work. Both of them would fail. Yep. Yeah, because now these are getting too big. Now this condition would start failing. All right. The number of undergraduates at Johns Hopkins University is approximately 2,000, while the number at Ohio State University is approximately 40,000. At both schools, simple random sample of about 3% of the undergraduates is taken. Each sample is used to estimate the proportion of all students at the university who own an iPod. Suppose that, in fact, 80% at both schools. Which of the following is the best conclusion? All right. Now, note here, they're talking about variability, okay? So these are comparing the variability of these 2 different schools, okay? Now, note that this proportion is the same, okay? So if we're comparing the variability between the 2 schools, let me go back and find the formula. If this is the same for both schools, wouldn't that mean this is also the same for both schools? Right? So what's the only difference between these schools? The sample size. Okay, population, ironically, actually doesn't matter. So it's about the sample size. So here, that 80% has nothing to do with the variability in this case, or I should say comparing the variabilities in this case. Really what we're looking for is the sample size. And we're told for the sample sizes, 3% of each population is a part of the sample. So which one has the bigger sample size? If 3% of each school got sampled, which one has the bigger sample size? Ohio. So Ohio had a bigger sample, right? What does that mean for its variability if its sample was bigger? It has smaller variability. Okay, so Ohio has a smaller variability than Johns Hopkins. So which answer mirrors what we just said? B. Johns Hopkins has more variability than Ohio State. The student newspaper at a large university asked a simple sample of 250 undergraduates, do you favor eliminating the carnival from the end of term celebration? All in all, 150 of the 250 are in favor. Suppose that, unknown to you, 55% of all undergraduates favor eliminating the carnival. If you took a very large number of simple random samples of size 250 from this population, the sampling distribution of the sample proportion, whoops, there should be a little P hat there, sorry, would be, all right, so first is asking, is it, oh, wait, there it is. I found it. It was sitting right there. Exactly normal, approximately normal, or we don't know. It's skewed. Okay? Well, to check if it's approximately normal or not, wouldn't that be taking the sample size times that true parameter and the sample size times the opposite of that true parameter? Yes. Actually, that's a great observation. So Tess just asked, could we eliminate the exactly normal right away? Would that be appropriate? Will anything ever be exactly normal? No. So I actually really like that observation. You're right. If it says exactly normal, it doesn't matter what the calculation says or not. You know that's not going to be the answer. Okay? Great. Even without doing the calculation, is it safe to say both of those are at least 10? Right? So are we okay saying this is approximately normal? Yes. All right. Where should it be centered? The 55, because it said this is the truth, right? And the center of the distribution should be the truth, okay? Now, just a side note, I know the standard deviations already match, but wouldn't this be how you calculate the standard deviation if we wanted to check that it actually is 0.03, right? And if you do that math, I'm very confident you would actually get the 0.03 that you were supposed to, okay? Is everybody with me? That's how you would calculate that. All right. Last one, and then I think we're done, aren't we? Oh, way to go, guys. All right. In 2010, a study of 240 randomly selected residents of a subtropical resort city with 82,000 residents found that 5.4% of them had been exposed to a mosquito-borne virus that causes dengue fever. I feel like I should actually know that. Anyway, suppose the actual percentage of people in the city who have been exposed to the virus is 3%. What is the probability of getting a sample of 240 residents where at least 5.4% of them were exposed? All right, so this is kind of what I was telling you about. Just, you know how to do the math, but now it's just figuring out how to show it as a multiple choice question. Okay, so aren't all of these, if we're calculating a probability and when we're sampling and make something normal, isn't this a normal probability calculation? Is everyone with me on that? Sampling leads to normal things. Any probability of a normal thing leads to this process. And along the way, what do we have to get to in order to calculate that probability? Z-score. So would you agree, actually, every single thing in here, isn't every single thing in there modeling taking a Z-score? Right? Is everybody with me on that? That's what you're looking at? You're looking at a Z-score calculation? Yeah? So, Z-score calculation says take the mean, or I'm sorry, take the observation minus the mean. What is our observation? Yeah, so this is our observation. This is the truth, the mean. Okay, so just looking at the tops, shouldn't the top of this thing be 0.054 minus 0.03? Yeah, so right away, don't we know A is wrong? And don't we know C is wrong? And don't we know E is wrong? Just because of the top, right? Now, let's look at the two we have left, okay? So the two that we have left, notice how they calculated the standard deviation. Notice the difference in how they calculated them. This one used the truth in that calculation. This one used our sample to calculate it. When calculating standard deviation of our sampling distribution, isn't the sampling distribution always based on truth? Right? So which one of those would actually be appropriate since we're basing this on a sampling distribution? D. Okay, this calculation standard deviation, you should be using what is supposed to be the truth in that calculation. Right, and again, I think, is that it, right? Yeah? Excellent. Way to be, guys. I'm sorry, I know that was kind of got to be a lot. All right, so let me get you your homework packet. No. It means I also don't do reading guides anymore. Sorry, man. Oh, I thought you were the only one that was reading. Granted, you also did super, super well, so there's something to that. All right, so again, just to note how next week is going to flow. So already Monday, we're going to review 7-2, and I'm going to give you the take-home quiz. What? Um, Tuesday, yeah, Tuesday I'm going to teach 7-3. Thursday, we're going to review 7-3, and then we're already going to start putting in motion, studying for this test. Okay? So again, I actually find this chapter really easy, and my kids last year all said, right, Maddie? Super easy chapter. Yes. But just again, do note it takes some keeping up because we do go through this very rapidly. Yes. So this is what my kids do. I mean, all these in Google Docs. This is me just coming at it. You could have been helping me because we had to like.
second one, I gotta shoot this video then.
The second day of school till the start of
So old, but obviously like not.
Crazy.
Like
so
I'm
he
like,
has a lot of time
why
to
do they look
refill.
old?
Right, Julia? Did he have a lot of time to like read the book?
It was so
Every Monday.
They just have less
Every
space.
So
Monday,
when
couple hours for reading.
so it was the summer before I time review. So it's when like I have John, Tyler, Evan,
Oh
Bradford
yeah.
crew, and I was at a family reunion. And my cousins are pretty like I mean I have cousins my age,
Yeah.
but then
Oh,
my
it's
mom is
Friday.
getting oldest, so I also have some pretty young cousins too.
Yeah.
And when they see them snapping to me, I think it was when John was, they looked at like, oh, is that one of your college friends? Like, he was my student. We did not go to college together.
Well, and
No.
you do look really young though, so
So it was so funny. I'm like, oh god, I love the age of my
they look
students.
old and you look young, so it like balances.
Have a good weekend.
Every time I visit the high school, I feel so it's weird because I like miss it, but I'm so glad I'm gone.
Totally did not get these.
Oh, thank you.
I was talking to Harper and she's like, so how you doing? I'm like, it's great not having deadlines except for like
Right?
exams and papers. That's my favorite part.
I need to go find Stroud now. I feel bad. I feel like he wasn't happy that I wouldn't go and talk to him.
Who was it?
And then the teacher that needed to talk with me.
Oh no.
Okay, the only
I know he sounded kind of, he was like, oh.
No, okay, the reason I was adamant against that though is when I'm filming, I don't know how to pause this, and if it's a confidential student, like
Oh
as a
yeah.
conversation about something confidential about a student, my kids would be able to hear it.
Yeah.
So I'll just go explain that to them. Like I wasn't trying to be rude. I just didn't want that conversation to be recorded when I can't stop it.
Yeah. That'd be bad.
Yeah, probably.